Hello teacher, so today I'll present our midterm report of web application development using Nodejs. Our team chose the Websockets topic. My team has two members, Nguyễn Lê Minh Khánh and me, and this is my file PDF. And in this report, we have five main contents. First, we will learn about the birth of Websockets. Next will be about Websocket protocol. Then we will talk about a Websocket API. Next, we will talk about Websocket SQL. And finally will be the demo code. And this is list of symbols and abbreviations. Here a list of tables, figures, and graphs. So let's talk about the birth of Websockets. During the 1990s, the web rapidly grew into the dominant way to exchange information. Increasing number of users become accustomed to the experience of browsing the web, while browser providers constantly release new features and enhancements. In this first chapter, we will look at how web technology evolved, culminating with the emergence of Websockets, a vastly superior improvement on HTTP or for building real-time web apps. About hatching the real-time web, the first web application started to appear in the late 1990s and used technologies like JavaScript and HTTP. We will now look at the main HTTP-centric design models that emerged for developing real-time apps, HAAS and Comet. So let's talk about HAAS. HAAS is a method of asynchronously exchanging data with a server in the background and updating parts of web page without the need for an entire page refresh. Let's look at how HAAS works by comparing it to the classic model of building the web app. And this is a classic model of a web app with the HAAS model. In a classic model, most user actions in UI trigger an HTTP request sent to the server. The server processes the request and returns the entire HTML page to the client. In comparison, HAAS introduces an intermediary between the user and the server. Although it might seem counterintuitive, the intermediary significantly improves responsiveness. Instead of loading the web page at the start of the session, the client calls the HAAS engine, which is responsible for regularly polling the server on the client's behalf, rendering the interface the user sees and updating it with data retrieved from the server. So we will move to Comet. Comet coined in 2006. Comet is a web application design model that allows a web server to push data to the browsers. Similar to HAAS, Comet enables asynchronous communication. Unlike classic HAAS, Comet uses long-lived HTTP connection to allow the server to push updates wherever they are available without the client explicitly requesting them. So several different techniques can be used to deliver the Comet model. The most well-known being long polling and HTTP streaming. Let's quickly review how these two work. So about long polling, is essentially a more efficient form of polling. Long polling is a technique where the server elects to hold the client's connection open for as long as possible, delivering a response only after data becomes available or a timeout threshold is reached. Upon receipt of the server response, the client usually issues another request immediately. Long polling is often implemented on the back of SMLH HTTP request, the same object that plays the key role in the AJAS model. This is a high-level overview of long polling. So let's move on to HTTP streaming, also known as HTTP server push. HTTP streaming is a data transfer technique that allows a web server to continuously send data to client over the site. A single HTTP connection that remains open indefinitely. Whenever there is an update available, the server sends a response and only closes the connection when explicitly told to do so. Yeah. So let's talk about a limitation of HTTP. HAA is and commit pave the way for reacting dynamic real-time web apps. However, even though they continue to be used nowadays, to lesser extent both HAAS and commit have their shortcomings. Hacking HTTP-based technologies to emulate the real-time web was found to lead to all sorts of drawbacks. We will now cover the main ones without being exhaustive. And this is a limitations of HTTP. Limited scalability, unreliable message ordering and delivery guarantees, latencies, and no bidirectional streaming. Yeah, this is a theories and defined. So I will pass this and move on to enter Websockets. So in 2008, the pain and limitations of using commit when implementing anything resembling real-time were being felt particularly keenly by developers, Microcarter and Anhison. Through collaboration on IRC and W3C mailing list, they came up with a plan to introduce a new standard for modern, truly real-time communication on the web. Thus, the name Websockets was coined. Yeah, this is our Websockets with the traditional HTTP request or response model. Yeah. The WebSocket technology includes two core building blocks. First is the WebSocket protocol, and second is the WebSocket API. And so I will comparing WebSocket and HTTP. While HTTP is request driven, WebSockets are event driven. The table below illustrates the fundamental differences between the two technologies. Here. Yeah. And let's talk about a use case and benefit when we using WebSockets. Yeah. So we can broadly group WebSockets use case into two distinct categories. First is real-time updates, and second is bidirectional communications. Yeah. So, and here are some of the main benefits of using WebSockets. First is improved performance. Second is extensibilities. And finally is fast reaction times. And this is the Bob supporting. Yes, here are some other benefits we gain by using buses. First is smoother scalability. Second is elasticity, and final is ease of development and fast iteration. So we will continue with the chapter 2 WebSocket protocol. Oh, first, we will talk about protocol overview. The WebSocket protocol enables ongoing full duplex bidirectional communication between web servers and web clients over an underlying TCP connection. Yeah, and here is a high-level overview of a WebSocket connection. About URL schemas and syntax, the WebSocket protocol defines two URL schemas for traffic between server and client. WS used for an encrypted connection, and WSS used for secure encrypted connection over transport layer security. Yeah. The rest of the WebSocket URL follows a generic syntax similar to HTTP. It consists of several components such as host, port, bus, and query as highlighted in the sample below. Here is scheme, here is host, port, here is path, and here is query. Yeah. It's worth mentioning that the port component is optional. The default is port 80 for WS and port 443 for WSS, and fragment in identifiers are not allowing WebSocket URIs. The hash character must be escaped as %23. Yeah. And let's move to opening handshake. The process of establishing a WebSocket connection is known as the opening handshake and consists of an HTTP 1.1 request response exchange between the client and the server. Yeah, let's talk about a client request. Here is a basic example for a GET request made by the client to initiate the opening handshake. Yeah. The request must contain the following headers: host, connection, array, set WebSocket version, set WebSocket key. In addition to the required headers, the request may also contain optional ones. Yeah. See the opening header session later in this chapter for more information on headers. And server response, the server must return an HTTP 101 tweeting protocol response code for the WebSocket connection to be successful and established. If stated code returned by the server is anything but HTTP 101 tweeting protocol, the handshake will fail, and the WebSocket connection will not be established. Oh, the table below describes the headers used by the client and the server during opening handshake. So let's talk about message frames. The WebSocket frame has a binary syntax and contains several pieces of information as shown in the following figure. And this is an anatomy of WebSocket frames. Now, let's quickly summarize them. FI and P indicates whether the frame is the final fragment in a WebSocket message. RSV 1, 2, 3 reserved for WebSocket extensions. Of course, it determines how to interpret the payload data, and mask indicates whether the payload is masked or not. Mask and key used to unmask the payload data. Payload length, the length of a payload. payload data consists of application and attention data. Yeah. Yeah. No. Let's move to upcoders. Every frame has an upcode that determines how to interpret that frame's payload data. The standard upcodes currently in use are the 5pi RFC, 64, 55, and maintained by IANA. Here is a frame upcodes. 8 glows, 9 ping, and 10 pong are Norris control frames, and they are used to communicate state about the WebSocket connection. Masking masking is used as a security mechanism that helps prevent cache poisoning. About payload length, the WebSocket protocol encodes the length of the payload data using a variable number of pis. Payload data, the WebSocket protocol supports two types of payload data text, UTF-8 Unicode text, and binary. Let's talk about closing handshake. Comparing to the opening handshake, the closing handshake is a much simpler process. Here is a closing handshake status code. Here is a define of sub protocol and extension. So I will move to security. In this session, we will cover some of the mechanisms you can use to secure WebSocket connection and communication over the WebSocket protocol. So let's start with the origin headers, which is sent by our browser client to the server during the opening handshake. The origin header is essential for securing cross-domain communication, especially if the origin indicated is unacceptable. The server can fail the handshake. These abilities can be extremely helpful in mitigating denial of service (DOS) attacks. So far, we cover security mechanisms that are used during connection establishment. Now, let's look at some aspects that impact security during data exchange between the client and the server. First of all, to reduce the chance of man-in-the-middle and eavesdropping attacks, it's recommended to use the WSS URI scheme, which uses TLS to encrypt the connection just like HTTPS. So we will talk about WebSocket API. This chapter we will introduce you to the WebSocket application programming interface, which extends the WebSocket protocol to web applications. The WebSocket API enables event-driven communication over the persistent connection. This allows you to build web apps that are truly real-time as less resource intensive on both the client and the server compared to HTTP techniques. In the following session, we'll look at the constituent components of a WebSocket API, its events, methods, and properties. So let's talk about the WebSocket server. A WebSocket server can be written in any server-side programming language that is capable of perfectly sockets. The server listens for incoming WebSocket connections using a standard TCP socket. Once the opening handshake has been recorded, the server must be able to send, receive, and process WebSocket messages. And let's move to the WebSocket constructor. To get started with the WebSocket API on the client side, the first thing to do is to instantiate a WebSocket object, which will automatically attempt to open the connection to the server. The WebSocket constructor contains a requirement parameter, the URL to the WebSocket server. Additionally, the optional protocols parameter may also be included to indicate one or more WebSocket sub-protocol that can be used during the client-server communication. Once the WebSocket object is created, then the connection is established, the client can start exchanging data with the server. The WebSocket API supports 4 types of events: open, message, error, and close. In JavaScript, WebSocket events can be handled by using on-event properties. For example, on open is used to handle open events. Alternatively, you can use an event listener method. Either way, your code will provide context that will execute every time an event is fired. Here's a defining of open, message, error, and close. About method, the WebSocket API supports 2 methods, ascend and close. So, once the connection has been established, you're almost ready to start sending and receiving messages to and from the WebSocket server. But before doing that, you first have to ensure that the connection is open and ready to receive messages. You can achieve this in 2 main ways. The first option is to trigger the send method from within the onOpen event handler, as demonstrated in the following example. The second way is to take the ready state property and choose to send data only when the WebSocket connection is open. The 2 code snippets about how to send text string messages. However, in addition to send string, you can also send binary data plug or array buffer, as so is this simple. After sending one or more messages, you can leave the WebSocket connection open for further data exchanges or call the close method to terminate it. Upon close, the close method is used to close the WebSocket connection. After this method is called, no more data can be sent or received over the WebSocket connection. If the connection is already closed, calling the close method does nothing. Here's the most basic example of calling the close method. Optionally, you can pass 2 arguments with the closed method, like call and reason. About properties, the WebSocket object exposes several properties containing details about the WebSocket connection. Firstly, priority time, buffer amount, extension on event properties, protocol, ready state, or URL. So in this part, we will find out together about WebSocket scale. First, the scalability of your server layer. There are 2 main paths you can take to scale your server layer. First is vertical scaling and second is horizontal scaling. And this is a vertical and horizontal scaling. So at first glance, vertical scaling seems attractive as it's easier to implement and maintain that horizontal scaling. You might even ask yourself how many WebSocket connections can one server handle. However, that's really the right question to ask, and that's because scaling up has some serious practical limitations. So let's look hypothetical example to demonstrate these drawbacks. Imagine you developed an interactive virtual events platform with WebSockets that's being used by tens of thousands of users, with more and more joining every day. This translates into an ever-growing number of WebSocket connections your server layer needs to handle. However, since you are only using one machine, there is a finite amount of resource you can add to it, which means you can only scale your server up to a finite capacity. Furthermore, what happens if at some point the number of concurrent WebSocket connections prove to be too much to handle for just one machine? Or what happens if you need to upgrade your server? With vertical scaling, you have a single point of failure, which will severely affect the availability of your system and the uptime of your virtual event platform. So let's talk about load balancing. Load balancing is the process of distributing incoming network traffic across a group of backend servers. When you scale horizontally, your load balancing strategy is fundamental. A load balancer, which can be a physical device and virtualized instead running on the specialized hardware or a software process, acts as a traffic hub sitting between client and your backend server farm. The load balancer receives and they routes incoming connection to available servers capable of handling them. And this is a load balancing. Load balancer detect the health of backend resource and do not send traffic to server that cannot deal with additional load. If a server goes down, the load balancer redirects its traffic to the remaining operational server when a new server is taken to the farm. The load balancer automatically starts distributing traffic to it. And the goal of an effective load balancing strategy is to provide for tolerance, high availability, and reliability. Ensure no one server is overworked, which can derail performance. Minimize server response time and maximize throughput. Allow you to flexibly add or remove servers as demand dictates. You can perform load balancing at different layers of an open system interconnection module. Layer 4 and layer 7. Yeah. And let's talk about a load balancing algorithm. The table below represents some of the most commonly used ones. Yeah. Architecting your system for scale. This is the book or sub-party. The book sub-parent decouple nature means your apps can theoretically scale to limitless subscribers. A significant advantage of adopting the parent is that you often have only one component that has to do with scaling WebSockets connection. The message broker, as long as the message broker can scale predictably and reliably, it's unlikely you have to add additional components or make any other changes to your system to deal with the unpredictable number of concurrent users connecting over WebSocket. Here are some benefits you gain by using PubSub. Smoother scalability, elasticity, ease of development, and fast iteration. And let's move to fallback transport. WebSockets suffer from network issues. Here are some of the problems you may come across. First is some processes don't support the WebSocket protocol or terminate persistent connection. Nextly, some corporate firewalls. And WebSockets do not entirely support Explorer or browser. If you foresee clients connecting from within corporate firewalls or otherwise strictly sourced, you need to consider supporting fallback transport. Yeah. And let's talk about managing WebSockets connection and messages. Yeah, yeah. Here are some of the things you can do to prepare for case where you have to deal with an extremely high number of WebSocket connection opening concurrently. First is testing and monitoring. Second is enforce limits. Last is ensure your system is highly available and fault tolerant. About monitoring WebSockets, here are some of a metric that are commonly monitored: number of connections, churn rate, message count, throughput, and network traffic, memory CPU uses, instance count, packet loads, duplication and reordering, latency, warning, and errors, server, data center, and region health. Let's talk about a load setting. Yeah, here are a few things to have in mind when setting connection. You need to run test to discover the maximum load that your system is generally able to handle. You need a backup mechanism for to prevent rejected client from attempting to reconnect immediately. And you might also consider dropping existing connection to reduce load on your system. And hardware, this is series. Yeah, so I will bust. Yeah, that's two. That two. And we will move to chapter 5 e-code demo. And in this session, we will demo codes based on what we have learned.
This is the demo of the WebSocket of our team. The first one I will introduce you about our code. Here we build a chart application to demo for the WebSocket, and we use socket.io to build this chart application. And we also add our database for the chart application. We start the message. Okay, and now we will rerun the code. This is the user interface of our chart. Here you can see that this display the total members in the chart. There is only one member because I just me access to the server, and here I can type the message and send the message to the community chart for everyone. Here it displays the name of the sender and the minute, then the time since I sent the message. Or I can also rename me. Here you can see here the name has trend, and also those messages have been stored on the database with some attribute name, message, and send time. This chart you can access this chart application from other browser. Here, when you access the chart, it will display the history of the chart for you. And the default name of you is anonymous. Here, because I've opened new window and access to the server, so increase the number of members in the chart to 2. Here I can type and send a message, and I back to the previous window, I can see that there's a message here sent from the second browser. So, and I can also open the open more browser access to the server and communicate with the community chat, or I can rename me here, and when I back to the previous chart, I can see the message from others. Okay, this is the end of the demo of our team.
Yeah, this is a reference and appendix. Yeah, this is all of my reports. So thanks for listening.